even and odd functions. Let's start with the definitions. So for some function f, we can say it is even f of x equals f of negative x. And then we can say it is odd if f of x equals negative f of negative x. Or an alternative definition we could look at is negative f of x equals f of negative x. Right? So just an equation manipulation there. And this definition needs to hold for all x in the domain of the function f. Now, it is possible for a function to be neither even or odd, so just keep that in mind. So what we're going to do is we're going to explain what these definitions mean and how to interpret them, and then how to apply them to some specific functions to determine whether or not they are even or odd. If we look at the even function definition, we have some starting function f of x, and we're told that for it to be even, it needs to equal f of negative x. Now, using our knowledge of transformations, we are aware that this negative x is a reflection over the y-axis, right? We have a horizontal reflection. So it's telling us that the original function, if we were to reflect it over the y-axis, it should look identical. Therefore, an even function has line symmetry about the y-axis as a result. So that's a nice visual tool to use to determine whether or not we have even or odd, or at least a starting point to lead you in the right direction when you're going to try to verify algebraically. So line symmetry about the y-axis, just for a quick example, some parabola maybe, where its minimum point is located directly on the y-axis, that would be an example of some line symmetry, where if I were to reflect this right side over to the left side, and then the left side back over to the right side, or do a complete line symmetry reflection over that y-axis, would it look identical to the original graph? And the answer would be yes in that case. So that would be what the even function shows visually. Now let's take a look at the odd definition. So I have two definitions here. Really, it's a preference thing, which one you prefer. The first definition, or even both, we'll explain both. So the first definition, we see again our knowledge of transformations. We can kind of figure out what this is going to tell us visually of what an odd function should look like. So that negative on the inside, multiplying the input value by -1, we know that's a reflection over the y-axis. But then multiplying the entire function by a -1 will result in a vertical reflection, this time over the x-axis. So it's telling us the original function, if we were to reflect it over the y and then reflect it over the x-axis, we should get an identical picture to the original graph. Now, doing these two reflections is synonymous with doing a 180-degree rotation about the origin. And therefore, we can say odd functions have point symmetry about 0, 0. The alternative definition over here, we can still see we have that horizontal reflection over the y-axis, and we still have the vertical reflection over the x-axis. So we're saying that if we were to look at the reflection over x and look at the reflection over y, would that result in the same figure? So that's your alternative definition. Quick example of what an odd function might look like. Let's just look at a basic cubic function, something like x cubed. Not the best picture, but that passes through 0, 0. Its point of inflection is located there. And we can see that if we were to do a 180-degree rotation, which means essentially if I were to flip this entire graph upside down, would it look identical to the original? The answer is yes. Okay, so we have some visual aids to help us determine if we think a function is likely to be even or odd, but what we need to do is confirm it algebraically, because what you'll see is sometimes the graphs look like they could be even or they could be odd, but we don't know for sure. They look like they might be off a little bit. Okay, so we want to be able to confirm algebraically, and the way we do that is through the definition. So what we're going to do now is look at some examples, and I'll walk you through how to confirm whether or not a function is even, odd, or again, it could be neither of the two. So if we look at example 1, we have f of x equals x cubed minus x. Now, if you have a graphing utility or tool to use, we could plug that in and just take a look at the graph. And when you do that, you're going to get a sense that this thing looks like it could be odd. So that's where we would want to start. So our odd definition tells us f of x, the original function, should be equal to negative f of negative x. So what we need to do is figure out what negative f of negative x equals. So what we can do first is determine, well, what's f of negative x? And all that means is we're going to replace our input values, x, with their negated value, negative x. So what that's going to look like is through a substitution on that original function, which was x cubed, we're going to have, or x cubed minus x, we're going to have negative x cubed minus negative x. So we made that initial substitution. Now, we have to negate the whole thing, but let's clean this up first. So negative x cubed is negative x cubed, and then negative of a negative is going to be plus x. So we found out what f of negative x is. Now, to fit the definition, we need to figure out what negative f of negative x is. So what we're going to do is multiply the entire function by negative 1. And we can see that that's going to equal x cubed minus x after the distribution. Therefore, negative f of negative x is x cubed minus x, which does equal the original function f of x, and therefore this function is odd. Let's take a look at number 2. We use our graphing utility. We plug in x to the 4th plus 1, and we're going to see something that looks like it has line symmetry about the y-axis. So our first thought is, let's check if this thing is even. Okay, again, we don't want to just go off the visual. We want to be able to confirm algebraically. So from the definition of even, f of x should equal f of negative x. So we already know what f of x is. We just have to determine, is f of negative x the same exact function after a simplification? So to find f of negative x, we're making a substitution. Again, if it's difficult to see, we're taking that x and we're going to replace all of them with negative x's in the function. So we had x to the 4th plus 1. So now what we're going to do is replace that x with a negative x. Now we're just going to clean this up. So negative x to the 4th is going to be x to the 4th plus 1. So we can see that f of negative x, x to the 4th plus 1, is equal to f of x, and therefore it is even by definition. Number 3, we have f of x equals 1 over x squared. When we graph, we're going to check to see if it's even based on the visual. So we want to see, is this true? So we have to find f of negative x, because we already know what f of x is defined for us. So we make a substitution of negative x in for x, and through the simplification, we can see that we get 1 over x squared, which is indeed equal to the original function f of x, and therefore this is an even function. Lastly, we'll take a look at this function. I think we're starting to get the idea here. So let's check if it's even. Let's say we didn't have a graphing calculator, we didn't know. So we're going to check even definition first. By the way, if you don't have a graphing calculator, because of how the definitions are, so there's our even definition, and here's our odd definition. Because the odd definition utilizes something that you would check even for, if you just check the even function first, that'll save you some time when you go over to the odd function. Or it doesn't, I guess it doesn't really matter, because you have to do f of negative x for both anyway. So let's go back to even. We know what f of x is. F of negative x would be 3 root negative x, which through a simplification would be this. Clearly not equal to f of x, so it is not even. So now let's check whether or not it's odd. So does this have point symmetry about the origin? We see that it does not have line symmetry about the y-axis. So we already know what f of negative x was, right? We verified that through even. Now, to check odd, we just have to negate that, right? We have to multiply it by -1. So negative 3i root x is clearly not equal to the original function. So it is not odd either. So this is our example of a function that is neither. And if you were to look at the picture, if you do have a graphing calculator, or if you wanted to plot it by hand, you would end up seeing a graph that's something like this. So we can see that there's no line symmetry about the y-axis, not even anything in this region or in this quadrant. And then 180-degree rotational symmetry, if we were to rotate this around the origin, we would get a result that looks like that. And you can see that that is clearly not the original function graph. So that's an example of a neither. So there's a basic overview of the definition for even and odd, and some examples on how to verify whether or not you have even, odd, or neither using the definition through algebra.